We've seen that the concept of the membrane time constant is useful for determining what the time course of a voltage change will be in a neuron. So for instance, when we activate a synapse and sodium ions flow into the neuron for, let's say, 1 millisecond, we can calculate what the time course of the voltage change in the postsynaptic cell will be by knowing the membrane time constant. So this is useful. However, if we are concerned about the propagation or passive conduction of synaptic potentials from the site of generation in the dendrite to the soma, we need to know how the amplitude of the synaptic potential will decay as it is passively propagated down the dendrite to the soma. And we can approach this problem in the same way that we calculated the time constant of the membrane, and that is to construct an equivalent circuit of the dendrite that will tell us how current flows through the cytoplasm and across the membrane of the dendrite as a synaptic potential is propagated down the dendrite. And we can do this first by dividing the dendrite into a series of segments and then constructing an equivalent circuit for each of these segments. So for this segment here, we can approximate this by a membrane resistance in parallel with the membrane capacitance. The membrane resistance represents all of the ion channels that are open in this segment of the membrane, and the capacitance represents the capacitance of this particular segment of the membrane. We then can add an RC circuit similar to this for each segment of the dendrite and connect them all together by resistances, which represent the resistivity of the cytoplasm of the dendrite, and also resistances that represent the resistance of extracellular space. Now, because the resistance of extracellular space is so low, we can actually represent these resistances as wires which have no resistance at all. So now all we have to do is solve for current flow through this admittedly quite complex circuit, and then we will know how a synaptic potential decreases in amplitude as it's conducted from the site of initiation towards the soma. Well, it turns out that this circuit has been solved. The current flow through the circuit was solved many, many years ago, in the 1860s, in fact, by none other than Lord Kelvin. And as you know, Lord Kelvin is famous for inventing temperature. And Lord Kelvin solved this circuit not because he was interested in current flow through dendrites of neurons, but because he was interested in current flow through cables, and specifically through cables that transmitted signals a long distance. In the 1860s was the first time that transatlantic cables were laid down to transmit first telegraph signals and then telephone signals. And as you can imagine, if you send a signal down a very long cable, it will decrement and the signal will die out fairly rapidly. So you have to add amplifiers at regular intervals, perhaps every couple of miles or so, to amplify the signal. And to know just how closely these amplification stations had to be placed, you have to know how quickly the signal will decay with distance, and that can be determined by forming an equivalent circuit of the cable, which it turns out is identical to the equivalent circuit of a dendrite. So Lord Kelvin solved for this circuit, and the series of equations that describe current flow through this circuit are called the cable equations, and we're going to consider just one specific case and look at the solution for this case. It simplifies the equations quite a bit. And this particular case is the following. We're going to have a synapse that's right here, and we're going to activate the synapse, and this, in contrast to a real synapse, will open up and current will flow into the cell, but we will keep this the channels open continually so that the voltage will depolarize, the membrane potential of this segment will depolarize and remain depolarized. Then the question that we'll ask is, how does this depolarization in this one segment, how does it travel down the dendrite? How quickly does the depolarization decay with distance? Well, the equation, which again is just one simplification of the total cable equations, is shown here, and this tells us that the voltage, the depolarization in the dendrite as a function of distance, equals the maximal depolarization at the site of generation times E minus x over lambda, where x is distance along the dendrite and lambda is the space constant, which is very similar. You can see this equation has a very similar form to the equation for the membrane time constant. And if we plot out this equation of voltage as a function of x, of distance, we find that if the depolarization was generated at x equals 0, and this was the V max, the maximal depolarization, as we measure the voltage as a function of distance down the dendrite, it decays as a first order exponential, as is described by this equation here. Now, just as the membrane time constant had a specific value tau, which described how quickly the voltage changed as a function of time, the lambda, the length constant, describes how the voltage decays as a function of distance. And in fact, the value of lambda, the length constant, tells us how far down the dendrite you have to be before the voltage drops to 1 over E, or 37%. So lambda tells us how quickly the voltage decays as a function of distance. We've seen that the time constant of the membrane can be defined and calculated from physical parameters of the neuron, specifically the membrane resistance and the membrane capacitance. In a similar way, the length constant of a neuron can be calculated from physical parameters, in this case the membrane resistance and the internal resistivity, or the cytoplasmic resistivity. And this equation here tells us the relation between the length constant lambda and these values. And very simply, lambda equals the square root of the membrane resistance divided by the internal resistivity. Now, just as we talked about specific membrane resistance when calculating the time constant and the specific membrane capacitance, we can define the length constant in terms of the specific membrane resistance and the specific membrane internal resistivity. And lambda in this case, which is in units of centimeters, equals 0.5 times the square root of the diameter of the process, the dendrite or the axon, and diameter would be in centimeters, times the specific membrane resistance divided by the internal resistivity. And if we examine this equation in more detail, I think you'll see that this makes sense in terms of conduction of a voltage down a process. So let's say we depolarize a segment at x equals 0 of a dendrite, and this depolarization decays as it passively spreads down the dendrite. Now, if the membrane of the dendrite were a better insulator, then you would imagine that the depolarization would spread farther down the dendrite. And in fact, that's what this equation tells us. If Rm, membrane resistance, is larger, that is, if the membrane's a better resistor, if the membrane has a higher resistance and is a better insulator, then the length constant will be larger. In a similar way, if Ri, the internal resistivity, were lower, that would mean the cytoplasm would be a better conductor, and you'd expect the depolarization to travel farther. And indeed, if Ri is smaller, then lambda is larger. And finally, if these values remain the same, the specific membrane resistance and the specific internal resistivity are the same, but we increase the diameter of the dendrite, then there's going to be a larger amount of cytoplasm. The cross-sectional area of the dendrite is larger, therefore there'll be more of a conductor, and the depolarization will be conducted further down the dendrite. And in fact, as the diameter increases, the length constant increases as the square root of the diameter. So I think you can say intuitively this equation makes sense. Now it's useful just as a exercise to look at the relation between the resistance of a segment and the specific resistance of that segment. And what we have down here are the equations that tell us the relation. So if we look at the membrane resistance of a specific segment, this equals the specific membrane resistance divided by pi times diameter. And if we look at values, the membrane resistance of a dendrite can vary from perhaps 100 to 100,000 ohm centimeter squared. We went through this exercise and saw these values before. The internal resistivity represents the resistance of the cytoplasm, and the specific resistance here is related to the resistance of a segment by this equation, where the resistance of a segment equals 4 times the specific internal resistivity divided by pi times diameter squared. The units of internal resistivity are a little strange. They're ohm centimeters. If you go through the details, you'll find that this is indeed the case. And the details of these equations are not that important for you to understand the concept of length constant and how it can determine and how it determines the passive conduction down the length of a process. But in fact, if you look at these equations and give it a little thought, you'll see that these relations are not all that complicated. We will be doing an exercise in class that illustrates how the length constant affects the passive conduction of a synaptic potential from the synapse down the dendrite to the cell body. And what we see here is the output of a computer program, Metaneuron, that we'll be using extensively in class over the next week. And it shows the generation of a synaptic potential, and it shows how it decays as a function of time along this axis, and also as a function of distance as the synaptic potential is passively conducted down the length of the dendrite. And what we'll be considering in the exercise is how this synaptic potential decays both in amplitude as it's passively conducted down the dendrite, and also how it slows up in time. And I'd like you to consider these, and we will be talking about this in class.